All right, we're going to move on with our work with multiplication properties of exponents, and we're going to look at a challenge problem and a real-world connection problem. I want you to try to pause the video and try these on your own, and then check back in, follow along, and see how you did. All right, so for this first one, we need to simplify, and it looks like we need to get a final single number as an answer. So no bases to powers or anything like that, just a single final number and no calculator allowed. And this looks absolutely intense. Huge exponents, so hopefully things will cancel out, simplify down, and let's see here. One thing I'm noticing right away is that these two powers are both going to be negative 80. And remember our rule that we briefly touched on earlier is that if we have different bases being multiplied to the same exponent, we can multiply those bases together. So that might be something that'll be handy. And that's looks like it might be what we want to do, because we have this 2 times 3 gets us this 6 over there. So it looks like we'll be able to do a lot of simplifying. So let's get started. And this is going to turn into 6 to the 5th, then 2 to the 4th is 16. Times 2 to the negative 80th times 3 to the negative 80th. Okay, anything to the negative 80th, by the way, is just a tiny, tiny number. But it looks like we can keep going here. This turns into 5 times 16 is 80, so 6 to the 80th times 2 to the negative 80th times 3 to the negative 80th. So it looks like we can do what we were proposing earlier, is multiply this 2 and this 3 together because the exponents are the same. Okay, so I'll try to write out all the steps here. This turns into 6 to the 80th times 2 times 3 to the negative 80th. All right, so it's 6 to the 80th times 6 to the negative 80th. And what does that turn into? We have common bases now. We're going to add those exponents together, and we get 6 to the 0, which is 1. So that was kind of cool, that really absolutely intense initial expression with huge exponents simplified all the way down to 1. All right, next one, the radius of the Earth. The radius of the Earth is 6.73 times 10 to the 6th meters. Okay, so that's about 10 to the 6th is a million, so about 6 million meters, right? Determine the volume of the Earth in cubic meters. Okay, so it looks like we're all set for units. We want to just take a radius of meters and get a volume of cubic meters, so we don't have to do any sort of conversion. Maybe you remember that the volume of a sphere is 4/3 pi r cubed. Okay, so let's just plug stuff in. I think we can do it. So we're going to get 4/3 pi times 6.73 times 10 to the 6th cubed. So remember, this cubed is applied to both pieces inside the parentheses. We're going to cube both pieces in there. Kind of like the distributive law, but don't officially think of it as a distribution. We're just applying the exponent to both pieces. So we have 4/3 pi times 6.73 cubed times 10. That's going to be 10 to the 18th right there. So let's do all this stuff. I need to pull out a calculator for that, and let's see what we get. And then we'll try to get our final answer written out. 4/3 times pi times 6.73 cubed. And so I get 1276.83. I'll round to a couple decimal places, and that's all times 10 to the 18th. All right, so we'd like to get a final answer in scientific notation. So this number that I'll highlight needs to be a number between 1 and 10, okay? And it's not, so we need to move the decimal place a little bit, 3 places. So we are going to move this 3 places, and we're basically dividing by 10 to the 3rd by moving the decimal place 3 places to the left, which means we can't just do that and have that be the only thing we do, because our number would change. We have to compensate for that. And over here, let's multiply by 10 to the 3rd. Okay, so we're going to get 1.27683 times 10 And this multiplication right here, we're just going to add those two exponents together, times 10 to the 21st, and that's going to be in cubic meters. So that's going to be our final answer right there. All right, and that's a good place to stop.